All right, so now let's consider another subject. Suppose we have a time-independent operator. So I'll write this time-independent operator, I will call it the operator A hat. And we want to consider the expectation value of this operator on a physical state. So recall the expression for our physical states, a psi of x and t, which will be the sum over an integer n, bn, e to the minus I en t over h bar psi n of x. So this is our physical state, and here is our time-independent operator. Examples of time-independent operators are x, the position operator, the momentum operator, the angular momentum operator. These are all time-independent operators. And now the expectation value of this operator evaluated on some state. You see, an expectation value of an operator doesn't have any meaning unless you say on what state you're computing that expectation value. So here we'll put the state psi of t. So this is a definition. And what are we supposed to do? We're supposed to calculate the following integral. All over space, the wave function psi of x and t, complex conjugate, and the operator acting on the same wave function to the right without complex conjugation. So this is the definition of the expectation value of the operator. And if we have an expansion of the state in terms of the energy eigenstates, we've denoted the little psi n's of x to be the energy eigenstates. Well, you can now substitute these sums into this integral and evaluate some of it. So let's do that. And in this expansion, we're going to substitute once a sum for psi star, once a sum for psi. So we have two sums. So I'm going to use two indices, n for one sum, m for the other sum. So what does this become? This becomes, if I try to evaluate, a sum over the integer n and the integer m. Now think of this, these are these sums. Now we have this number. So since we use n for the psi star, we have bn star. For the other one, we have bm. So those are the sums. Now we have integrals over position, and these factors don't have position dependence. So we have e to the I en t over h bar. See that we're complex conjugating, so this sign has changed. We have e to the minus I em t over h bar. And then we still have the integral to do, integral from minus infinity to infinity dx psi n star of x a hat psi m of x. So you should look at this expression and try to make sure you understand where every term comes from. One important thing is that this is a time-independent operator and doesn't act on time, has nothing to do with time. Time never features here. And therefore, the exponentials of time in the wave function just went out. They're out of the integral. So we can do a little bit more of simplification, not much more really here, but we can write it slightly better. So we're just going to continue here and just write a hat in psi of x and t is equal to sum over n and m Bn star Bm. And let's put these two exponentials together. E to the I En minus Em t over h bar. And we have this integral minus infinity to infinity dx psi n star of x a hat on psi m of x. So a little cleaning, nothing much. And that's as far as we can go now, unless you tell me what this operator A is. So unless I know what it is, I don't know how it acts on this wave function, and therefore I cannot evaluate the integral and cannot simplify it anymore. So recall, this is a time-independent operator, could be the position operator, would be an x that would be multiplying here, momentum operator, any time-independent operator. So we'll try this for the Hamiltonian. The Hamiltonian, let's consider a time-independent Hamiltonian, and that's a really interesting operator, so we would like to get some idea of what this is for the Hamiltonian. So try h. So the expectation value of h hat on the state psi would be, now I would have to put instead of a, just h. So let's look just at this piece. What would it become when a is h? Well, you would have the integral from minus infinity to infinity dx psi n star of x h psi m of x. But these little psi's were defined to be eigenstates of the Hamiltonian. So this thing is Em times psi m. And the integral of psi n star psi m by orthogonality is just a delta function. So this whole thing is just equal to Em times delta mn. The Em is a number that comes out, the integral of the psi's gives you this. So using this result, this double sum becomes a single sum in which every m index can be replaced by an n index. And what happens then? Well, you just get sum over one index, and m becomes n. So this thing becomes the norm of Bn squared. Em becomes En. And the exponential, since n is equal to m, vanishes. So this is 0, this factor becomes 1, and that's all that is left. Now, I want to emphasize one thing. This is a time-independent operator, and we're evaluating its expectation value on a time-dependent state. Therefore, this result is generally time-dependent. Those expectation values can have time dependence. They're operators, the state is changing. The position operator on a particle that is moving would have a time-dependent expectation value. So in general, this is time-dependent. But when we try the Hamiltonian, a time-independent Hamiltonian, it is, in fact, time-independent. Now, if it's time-independent, it means something, and in this case, it means the energy is conserved. Moreover, here you get an intuition about what is the expected value of the energy that you would measure, and for each energy eigenstate n, you get that value weighted by the amplitude, by the probability that you be found on that state. When we wrote this expansion upstairs of the wave function in terms of energy eigenstates, these coefficients Bn represented the amplitude to be found in that energy eigenstate. So this is a reasonable thing. I want to conclude this point with one more discussion, one more comment. In this calculation, in this definition of the expectation value, we have assumed that the state psi is a normalized state. This formula is not true if the state psi is not normalized. So sometimes you don't want to take the trouble to normalize a state. So what can you do if the state is normalizable but not normalized? So let's do that. So suppose the state psi of x and t is normalizable. It can be normalized, but it is not normalized at this moment. If it is not normalized, if you computed the integral from minus infinity to infinity of psi star of x and t, psi of x and t, this number is not 1. If it's 1, it's because it's normalized. But if it's not 1, it would be a number n, which is a real number, positive. And the fact that it's a finite number means that this wave function can be normalized. In fact, you studied before that even though there's time dependence in the integrand, there shouldn't be time dependence in this integral, and this is guaranteed by the Schrödinger equation. So this is a number that is time independent, and that's it. So if this wave function is normalizable, then if we call this n, the wave function psi of x and t divided by square root of this number is normalized. This is the normalized version of this wave function. Why? Because if you do exactly the same thing of evaluating this integral, but for this whole object, you'll get the integral of psi star psi in the numerator, which is n, and you'll get 2 factors of square root of n that will cancel. So this is normalized. So if I encounter the definition of the expectation value of A, and I don't have a normalized wave function, I just have a normalizable wave function, instead of putting psi here, I should put the normalized thing in this definition. So this whole thing is what must go into this formula up here for the expectation value. As a result, the expectation value then takes the form minus infinity to infinity psi star of x and t dx a hat psi of x and t, and a factor of n, because there are 2 times the wave function, in the denominator. So in order to write it perhaps a little more elegantly, we'll just write another integral dx of psi star of xt psi of x and t. And this is a formula for the expectation value of a time-independent operator in the case that you're working with a wave function that is normalizable but not normalized. So it's a slight generalization of the formula over here.